apples are delicious. If you make this statement in a grocery store, you will probably get nods of agreement. If you make it to a botanist, you might start an argument. What exactly defines some? And who decides what counts as delicious? In normal conversation, human language relies heavily on context and assumption to bridge these gaps. We need a way to strip away the poetry and ambiguity of English and map those ideas onto a framework of strict, undeniable mathematical truth. To build that map, we have to look closely at how a computer actually evaluates a true or false statement and examine exactly where our oldest logical tools hit a wall. For decades, the foundational operating system of mathematics has been propositional logic. It evaluates complete, closed statements. Take the equation 2 + 2 = 4. All the required information is present. The system weighs it, the logic checks out, and it outputs a definitive true. But the system breaks the moment we introduce an unknown element. Consider the statement, x is greater than 3. Is that true, or is it false? The system freezes. Without knowing the exact numerical value of x, basic logic cannot make a ruling. The real world does not operate on closed, static equations. Reality is a complex network of unknown and shifting variables. To process it, we need an entirely different tier of logical architecture. That architecture is predicate logic. It resolves the x problem by splitting a mathematical statement into two distinct functional components. The first component is the predicate, represented here by a capital P. You can think of the predicate as the action, or the specific property we want to test. In our previous example, the predicate is the rule is greater than 3. The second component is the variable, the x inside the parentheses. This is an empty slot waiting for whatever real-world object or number we want to evaluate. Once we plug an object into the variable slot, the statement immediately snaps into a proposition. Plug in a 4, and the output is true. Plug in a 2, and the output is false. We can expand this template to handle multiple variables at once, like q of x, y, allowing us to map relationships between entirely different objects. We can use this to map a human interaction. If we define the predicate as asked a question, we can set x to represent Lois and y to represent Professor Michael. We have translated the English sentence, Lois asked Professor Michael a question, into a verifiable logic state. This gives us a precise way to test individual relationships. But if you are analyzing a massive database of students and professors, you cannot manually test every single interaction one by one. You need a mechanism to apply these rules across entire populations. To evaluate at scale, predicate logic introduces a set of parameters called quantifiers. They define exactly how far a predicate's rule should stretch across a given domain. The first is the universal quantifier, symbolized by an upside-down A. This acts as a strict filter, declaring that a specific rule holds true for all elements under consideration. If we want to capture the absolute rule, all rabbits are faster than all tortoises, the universal quantifier lets us define all x in the domain of rabbits and all y in the domain of tortoises, locking in the speed relationship across both groups. The second tool is the existential quantifier, written as a backwards E. This is a much looser search parameter. It simply means there exists, or some. This handles exceptions without breaking the system. If you input the phrase, "some birds cannot fly," the existential quantifier confirms the statement is mathematically sound as long as it finds at least one penguin or ostrich in your dataset. By combining predicates to establish the rules and quantifiers to set the boundaries, we have assembled a translation engine. We can now take qualitative observations from the physical world and formalize them. Let's put this engine to the ultimate test. We will feed it an English sentence containing overlapping actions, multiple actors, and complex grammatical conditions. Consider this phrasing. Every faculty member has either asked Professor Miller a question or been asked a question by Professor Miller. To translate, every faculty member deploys a universal quantifier for variable x. We map the two-way relationship, x asked Miller or Miller asked x, linking them with a logical OR operator. The result is a precise string of nested quantifiers, converting a human sentence into pure mathematics. Stripping away the grammatical noise and human subjectivity, we are left with a raw logical framework. This is a statement that any computational system can instantly verify without the risk of bias or misinterpretation. This process powers modern technology directly. When a global database cross-references millions of user records, or an AI model evaluates complex relation predicate logic, it acts as the necessary bridge, carrying the chaotic elements of reality into the structured realm of pure computation. Albert Einstein once observed, "Logic will get you from A to B. Imagination will take you everywhere." By establishing absolute, verifiable proof for point A and point B, predicate logic secures our intellectual baseline. Once that rigorous foundation is built, we are free to construct, compute, and imagine the rest of the universe on top of it.